so we can try and keep everything on time. Hopefully the other two authors will be able to do a quick changeover when they bring their presentations. My name is Jeff Crompton. I'm with Alcim Technologies, and we have a very big interest in some of the areas that are being covered today in this area of bioscience and bioengineering. It's one of the main areas that we do our consulting work in, so it's a pleasure to be part of this and to learn from the other presenters that are going to be here this afternoon. So our first presentation today is on the thermal simulation of breast tumors by Francisco Gonzalez. So Francisco, if you would like to come up and share with us what you've been doing.
Thank you very much, Jeff, for the introduction. My name is Francisco Javier Gonzalez. I go by my middle name, which is Javier, but Francisco's fine too. And I'm going to present here work I've done over the span of 10 years, starting at the University of San Luis Potosí in Mexico, and now as a consultant of a company in Mexico called COMSOL. And I'm going to talk to you about thermal simulations on breast tumors. Basically, the main goal is to advance the technology, which is usually called as an optical biopsy. Usually when you want to see if a piece of tissue it has a disease or not, they take out that tissue, look at it in the microscope, and see if there's something wrong with it. So ideally, it would be better if you didn't have to cut the piece out, and so by using optical techniques, you can do an optical biopsy, which is called an optical biopsy. Here are 3 examples of optical instruments used for this purpose. A Raman spectrometer with diffuse reflectance spectroscopy, but I'm going to talk about thermal patterns. And as you guys already know, temperature has been a variable of interest in medicine for basically forever. It's been used as a sign of illness and also a way to monitor the progress of a disease. And it happens that the skin the human skin is a very good thermal radiator. It has an emissivity almost close to 1, which is basically a black body, and it doesn't depend on the color of the skin. If it's a kid or an older person, the emissivity doesn't change. So it's infrared imaging. It's a very good way to measure temperature patterns in the surface of the skin. And also we have that, in particular breast tumors, which is what I'm going to talk about here, since they have a faster growth rate, they have a higher metabolic heat generation, and they also, in order to keep that higher growth rate, they need more food, right? So there's a process called angiogenesis that takes place inside the tumor to increase the blood flow in the tumor and get more food to the in this case, tumoral cells. And this increase in metabolism and perfusion makes that those tumors have a higher temperature than normal tissue. And those increases in temperature can be measured with an infrared imaging system. Here's a couple of thermographies taken on a healthy person. As you can see, in the healthy person, there's a very distinct symmetry in the temperature pattern between one breast and the other one, and in a person with a cancerous tumor, there's a distinct asymmetry and an increase in temperature. This work is based on work that was done in the 70s by Gauthiery. He, during 14 years, analyzed 58,000 patients using temperature patterns. 4,000 of them had cancer. And he also managed to get 147 extremely brave women to put a needle inside their breast with a temperature sensor in the tip without anesthesia, because that would change the blood flow, and measure the temperature as a function of depth in the breast. And that gave us great experimental results for temperature patterns. Here we can see the temperature profiles of a healthy person and a person with cancer. So as you can see, here in a healthy person, the temperature, the temperature at the surface of the skin is 32 degrees C, but in the case of a person with breast cancer, the temperature at the surface of the skin increases 2 degrees C. And also, the profile is different. They all reach the core temperature at the chest wall, but there's also an increasing temperature here where the tumor is. So also Guattari published that tumors that are more malignant, that they double their volume in less time, have a higher metabolic rate than those that they don't grow as fast. So that would be, heat generation would be a way to determine malignancy in a tumor, for example. So basing our work in that seminal paper, we started doing finite element simulations using the Pence equation, which is basically the heat diffusion equation with two extra terms, which is the metabolic heat generation and the perfusion term. And we pulled all these values from the literature. We started working on this problem like 10 years ago. 10 years ago, there wasn't a bioheat transfer module in COMSOL, so you had to plug in directly those extra terms. And well, we started with a very basic model. It's a hemisphere and a tumor model as a sphere inside the hemisphere, and the chest wall, it was that plate. We set up our boundary conditions, and we solved the bioheat transfer equation. We could see that, well, effectively we got an increase in temperature in when we had a tumor as opposed to when we didn't have a tumor, and we matched those results with the experimental results that Guattari published in 1980. We also figured out, well, we made some calculations on what would be the smallest tumor that thermography could detect with modern infrared imaging systems. For example, one with a thermal sensitivity of 20 millikelvin, we would detect a tumor 5 millimeters in diameter, 2 centimeters deep in breast, which is good because it's the minimum size you can feel like something in your breast is around 1 centimeter. The thing is that, as you can see, that this is a very crude model. I mean, it's basically a very crude approximation of how a breast looks. There's some thermal particularities on the thermography that they do not appear in a perfect sphere. So the next step was to try with a more realistic model. So we downloaded this model from the internet. It's basically an artistic rendition of a female torso. We repeated the same simulations, now using the bioheat transfer module. And as you can see, we get a more realistic thermal pattern in this case. If we compare, for example, the thermal pattern of this simulation with an actual thermography, you can see that there's a very good resemblance between one and the other. We did some parametric simulations on this model. We simulated several tumors, or also malignant and benign tumors, which is basically cancerous tumors and cysts. On this model, this is the temperature profile on a healthy breast and one with a breast tumor, and we found out that there was a different difference in temperature between one breast and the other if the tumor was malignant or we had actually a cyst. The thing is that we weren't happy with these results, so we tried to scan, make a 3D scan of a real patient with breast cancer. This is a video of how the scanning procedure was performed. I don't know exactly the particularities of this process. We did it through a company that specializes on doing 3D scans for prostheses and that kind of medical stuff. But by doing a 3D scan, we can make simulations on exactly the same model we were analyzing. We imported the model in this case as an STL file, and we performed our simulation. So as you can see, in the case of a healthy person with this torso, you had this type of temperature profile. If we put like a 2.5 centimeter tumor on the right breast, you can see the increase in temperature in this case. And if we compare the temperature simulations with the actual temperature pattern taken with an infrared thermal camera, you can see, well, there's kind of a resemblance. So here's where the future work comes into play. The next step, which I'm not going to present unfortunately in this conference, is try to include internal structures in the breast. We believe that by including internal structures of the breast, we would get a closer temperature pattern compared to the real pattern. And well, as the conclusions, we use finite element simulations to predict thermal patterns of healthy and diseased torsos. And in the future, we hope that including internal structures, we can more faithfully analyze and compare those thermal patterns to actual infrared thermographies. Thank you very much.
Thank you. Okay, I think we have time for a couple of questions. Oh, we have lots of questions. Okay, let's start over there, Josh.
How do you know that in 1480 BC that you were doing temperature to measure disease?
That's actually a great question. But and there's account that Hippocrates in that era he used mud and put mud on his patients and look where was the region that dried first, and he knew the problem was there. So that's how he figured out that the temperature was an issue in this case. But that's a great question.
Okay, I think we have one at the front here.
Thank you. It's a very nice work. So I have several questions. The first one, where did you get the perfusion data? So
There's I actually have a couple of papers where I use the perfusion, and the references there, so I can send you the papers later. But they're in the literature.
so you did it in your
Yes.
And there is another question which I have. Like, this is the application is just to diagnose the cancer, right?
Well, I wouldn't say diagnose. It would be that there's something wrong with the breast, because there's a lot of things that change the temperature of the breast. One of them could be breast cancer, but yeah, to monitor breast health, I would say.
Okay, monitoring, you mean like controlling the growth of the cancer cells?
Say again?
So you are looking for how it grows, right? The cancer.
Yeah.
Thank you.
I think we have one question in the back there.
So thank you for your presentation. I was wondering from the simulation standpoint, what condition is different for a tumor versus what is different between them when you're setting up your simulation?
That's a very good question. For example, a tumor has a lot of vascularity, so the perfusion rate is really high, and in a cyst basically it doesn't have any veins or whatever, so the perfusion is basically zero. So that's why it looks colder than a tumor.
All right, thank you very much, Javier.